distortion in weldment also a consequence of the residual stresses developed during the welding process, but the main reason for the distortion in the weldment structure is mainly the solidification shrinkage, any thermal contraction, and of course, metallurgical changes also happens during the welding process, and if there is any boundary constraints, all this actually influence the distortion in the finite weld joint structure. So, the reasons for the distortion in weldment is very similar to the reasons for the generation of the residual stress in welding. So, that is why always we usually used to say that distortion and residual stress in welded structure, they are linked with respect to each other. Now, how we can measure or how we can quantify the distortion in a weld joint. So, if you look into try to do some butt joint configuration, then main straightforward way to measure the specifically the angular distortion during the welding. So, angular distortion can be measured even for the welding of the very thick plate or maybe welding of the very thin plate. So, figure shows that first figure the transverse shrinkage in a butt joint configuration, that transverse shrinkage if it can be a concave or convex type of buckling also occur within the welded structure depending upon the types of materials. And if you look into that figure, the angular change in a butt joint. So, simply assuming the along the longitudinal direction the plate is very straight and there is only the angular distortion, and that we can measure it. Or angular change in the T joint may also happens during the welded structure, and longitudinal direction in a fillet joint also it bends or buckling may happens corresponds to the kind of convex kind of structure. So, depending upon the whether the distortion is with can happen in a concave type or convex type or maybe straightforward simply angular distortion, all can be measured in straightforward using probably we can use it simple coordinate measuring machine or some laser scanning system. With respect to some reference point we can measure the distortion. But what is the reason for this generation of the distortion? The welded component basically can shrink in the different direction depending upon the weld nature of the type of the weld joint, and that means both transverse as well as longitudinal direction the deformation may also happen. So, buckling may also happens, and accordingly we can classify the different types of the distortion in a welded structure. Here if you see that right hand side the figure indicates the actual joining of the titanium alloy using the plasma micro welding process, and here only the thickness of the plate is 0.5 millimeter. That means it can be considered as a joining of very thin sheet. So, in this case we can see that the deformation is the concave convex type depending upon which and whether we are looking in the along the transverse direction or whether we look into the along the longitudinal or welding direction. So, in this case it is wise to measure the distortion not in terms of the angular distortion, but more accurate measurement of the distortion can be done if we locate the several points on this weld, and then if we try to measure the different point, probably we can measure the distribution of the distortion at the throughout the whole structure. But it is a simplified way, we can measure only on the angular distortion. So, with respect to the initial position and after the butt welding, what is the distortion of the plate happens, and that can be measured in terms of the D as shown in the figure. So, this is the way to measure the distortion, but what way we can reduce the distortion, because this amount of the distortion is a very serious problem in the welding process, and this actually creates the dimensional accuracy when two different components we are trying to join this. So, there are several ways to reduce this amount of the distortion. One is that by reducing the weld metal volume. So, that means melting volume of the material, if it is less amount, then probably we can reduce the distortion. Of course, in this case the less amount volume, less amount of the molten pool volume, but at the same time it should attain the full depth of penetration. In case of using electron or laser beam welding, the maybe the solution, because in this case the oil pool volume is relatively small as compared to the other gas or arc welding processes. So, therefore, laser welding or electron beam welding is the one solution to minimize the angular distortion or other kind of the distortion in welding process. Placing oils above the neutral axis, if we when you try to do kind of V joint kind of this thing. So, there is a the volume of the oil pool metals not this is a not uniform throughout the depth of penetration structure, it varies from maximum to the minimum point. So, with respect to that type of cross section, if it is possible to place the equilibrate amount of the oil pool volume with respect to the neutral axis, then probably in that case that the amount of the distortion can be reduced. And of course, one very large structure or maybe in a very complicated, that following the multipath or multipass welding process, the distortion can be controlled. So, multipath means if you use the laser scanning or using the laser welding throughout the structure and following some specific pattern of the scanning of the laser on the surface, and the path can be different. So, designing the path, probably we can reduce the amount of the distortion, or sometimes in case of multipass welding, not placing the or supplying the molten material within the oil pool volume, not only on the single pass. If you, it can be filled by using the several passes, probably in this case the amount of the distortion can be reduced, and this multipass welding process mainly happens very high thick material. So, these are the very straightforward way to reduce the distortion of the different welded structure. Now, other type of methodology also exists to reduce the amount of the distortion. If we simply look into this figure, that presence of only single V, that means one sided, and welding of this thing can definitely most of the cases it will produce some angular distortion. Specifically, the angular distortion is mainly happens when the thickness of the plate is relatively high, and in this case, if the similar kind of similar kind of oil pool volume can be placed in the both sides of the plate, then it will try to neutralize the amount of the angular distortion, or it can be reduced the amount of the angular distortion. It is very obvious from this the figure. So, therefore, welding alternately on the either side of the double V joint is preferred to reduce the distortion. And another mechanical way to that, by using the elastic pre-spring before the welding, can also helps to reduce the angular joint. That means, simply that before welding some angular, intentionally you could give some angular distortion, and if you do the welding joint, so that after welding it can try to neutralize the pre-existing angular distortion of the weld joint. So, that is the one way to reduce the distortion. Definitely preheating, sometimes the preheating of the material before welding can also reduce reduce the distortion. Thermal management during welding, that means it is possible to control the thermal cycle, that means time temperature cycle during the welding process, that also influence the distortion level of the weld joint. And of course, post weld heat treatment or post weld heating also sometimes reduce the angular distortion. So, that means it is a very straightforward way using some mechanical means, for example, pre-straining or pre-springing angular changes can reduce the distortion, but at the same time the distortion also affected by the some metallurgical changes, and that metallurgical changes is very much influenced by the thermal cycle in the welding process. Thermal cycle means the time versus temperature cycle. So, by proper control of this time versus temperature cycle, or we can say the thermal management of the during the welding process, that helps to reduce the amount of the distortion. Apart from that, preheating or post heating also helps to reduce the distortion level simply by changing by the microstructure of the welded joint. So, these are the typical methods for reducing the distortion level in a welded structure. Now, we come to that point that one significant or important part, that is the welding solidification in welding process. So, definitely the molten pool with when come in contact with the some cooling medium, and most of the cases is the open atmosphere, and that or it is also sometimes under the shielding gas, or maybe in sometimes it can be done in a closed chamber also. So, anyway, some kind of cooling medium exists. So, the molten pool gradually solidify and come back to the ambient temperature, or maybe come back to the service temperature. So, that during the cooling period, the what is the thermal cycle, time temperature cycle, and what is the rate of cooling, that is very much significant or important in the solidification process of the welding in any welding process. So, because the solidified structure is actually decides the mechanical properties of the weld joint. So, it is very much necessary to understand the solidification behavior in welding process. Now, there are several solidification theory, but our focus is only in specific to the welding process. So, here if you see the mode of the solidification, that what is the final shape and size of the welded microstructure, that can be seen that mode of the that depends on the mode of the solidification. So, therefore, temperature, the solidification happens, the temperature of the weld pool comes from superheating temperature to the phase transformation temperature, basically solid state phase transfer from liquid to solid phase transformation temperature, and then gradually cooling from that solid gas temperature to the ambient temperature. So, throughout this process there may be the several phase transformation may occurs, and specifically that phase transformation not only the liquid to solid phase, but in case of alloy there is a solid state phase transformation may also occur. Now, if we look into that typical the time temperature curve in solidification process, if we look into the specific pure metal, we know the basic elementary curve for the time versus temperature. So, first curve is first figure is shows that in case of the pure metal, when you try to follow the cooling from the some superheated temperature, and then when it comes to the melting point temperature, there is a some time lag, or maybe some time is required to change the phase without changing the temperature. So, that melting at the melting point of the specific pure metal. So, specifically in case of the pure metal, there is a single point there is a single melting point temperature. So, that means the from liquid molten pool to the solid material may happens over a single temperature, but over a lapse of time. So, that lapse of time is basically the release the specifically a latent heat by changing the phase from liquid to solid phase. So, that graph clearly shows that there is a phase change over time, and from liquid to solid, and gradually in the solid state there is a considerable decrement of the time. So, this is a typical solidification curve in case of the pure metal. But if we look into that cooling curve of the alloy system, so in this case specifically the alloy system, or it is easy to explain the alloy system if we consider the binary alloy. So, in this case the time versus temperature, if we see that it starts from the superheating temperature, and one that is a liquidous temperature, and there is a two defined temperature over which the solidification happens. That means, from between the liquidous temperature to the solidus temperature. So, between these two is normally called the Mossi zone. So, the mixing of the solid and the liquid phase exists between these two temperatures, solidus temperature and liquidus temperature. So, like pure metal, the phase transformation from liquid phase to the solid phase does not happen on a single point temperature. Rather, it happens over a range of the temperature. So, within this range of the temperature, of course, the phase change happens from liquid to solid phase, and these are the typical cooling curve or time temperature cycle in case of alloy material, alloy system. So, with this basic understanding of the cooling curve, we will try to explain the solidification behavior of the in case of the welding process. Now, more intuitively, if we look into that cooling curve of an binary alloy. So, we assume that it is a binary alloy, there is a two they are soluble, completely soluble with respect to the each other. Now, if we start the temperature versus time, here we can draw these two curve. So, we can say that first curve, one part, that convex part is the basically the liquidus temperature, and concave part is basically the solidus temperature. That means, within this there is a change of the phase from the, it starts from the liquid phase and then comes to the solid phase. But here there are two components are there. So, this is a specific alloy system. So, in this case, if we look into at point A is a single point. So, that single point actually indicates the melting point of the component A. So, that means of the component A means here it indicates that it is a pure metal. So, on this pure metal it follows the simply cooling curve like that at this point if it is a 100% composition of the single component, then here if you see that the phase change happens over a range, phase change happens one constant temperature, and then afterwards it after cooling it comes to the ambient temperature. But similarly, if you look into the point B also, here we can see that at point B it is also pure metal, but the different metal. So, here the melting point are different as compared to the metal A. So, here also you can see that phase change also happens over a range of the time, but at constant temperature. So, it follows the similar kind of the cooling curve like the pure metal A. Now, if the alloy system consists of the material A and B, it is a mixing of this thing. So, it becomes alloy. So, in this case the phase change starts at point at this point. So, that actually exactly on the liquidus line. So, here at this point it just starts from the changes of the phase from liquid phase to the solid phase. So, the change of the phase happens over a range of temperature, and here correspond to this is the solidus temperature, and here it is the corresponds to the liquidus temperature. So, it starts from the liquidus temperatures and comes to the solidus temperature, and that phase change happens with this range of the temperature, because it is an alloy system. So, binary alloy system, it consists of the component A and B, and that in that way we can represent that different cooling curve if there is a change of the composition. So, here basically the pure 100% A composition, here at this point the 100% B. So, both the cases we can consider as a pure metal, but in between any stage this is the certain percentage of the A and certain percentage of the B, they constitute some alloy system, and that alloy system actually change the phase from solid phase to liquid phase to solid phase, and that actually happens over a range of the temperature. So, this is the time versus representation of the typical temperature versus time. But if we look into that temperature versus composition, here we can see that x axis actually represents the composition. So, here A at this point it is basically exactly 100% A, that means we can say it is a pure metal at point A. Similarly, at B 100% composition is 100% B, that means it is a pure metal B, but in between there is a mixture of A and B, certain percentage of A and certain percentage of B exists. So, at any point we can define this is the if you draw any vertical line. So, that actually represents the composition that consists of A plus B, and any proportional way may be different at the different point. So, it starts from 100% A, gradually if you moves towards the x towards the positive direction. So, towards the B, then here percentage of A actually decreasing, and gradually here the A is the 100%, and here at this point A is basically 0%. Similarly, if we move in other direction, B is 100% and here B is the 0%. So, in that way we try to represent the composition along the x axis of an alloy system. So, this alloy system, and if we at intermediate point at any point, its alloy system consists of A plus B. So, here this point starts the solidification and it's solidify, it's a completely becomes the completely solidified. So, in between there is a mixture of the solid phase and the liquid phase actually coexist, that the two different line. So, this line is basically represents the liquid gas temperature line, and this line curve basically represents the solid gas temperature line. So, in this the simplified way we can represent the cooling curve of an alloy system. Now, we look in further analysis of that. Now, that basic understanding of the solidification in welding process. So, how it happens in case of the solidification process. So, in this case mainly the driving forces is in the solidification of the, we will just try to look into the solidification of the pure metal. So, here the driving force is mainly the undercooling or supercooling. We will come back to that analysis of the undercooling and the supercooling. So, in this case the solidification mainly happens in the two phase. First is the nucleation, and that means phase transformation may happens in this two phase, the nucleation and then subsequently growth. And nucleation basically involves that the formation of the small stable particles, that is called nuclei of the new phase from the liquid. So, if we look into that picture, so suppose this is the liquid metal. So, when this liquid metal exactly comes from superheat temperature to the liquid gas temperature. So, then there is a start of the formation of the small nuclei, small particle, and that particle and the liquid metal actually coexist. And after certain, when it crosses the solid gas temperature, then the consist of the all are the solid particles, but that afterwards the solid particles may also grow, and it will try to consume the completely replaced by the liquid phase molten metal. So, in the growth stage basically the stable nuclear size is mainly increases as a result of the parent phase, and that gradually that parent phase basically liquid phase gradually disappears. So, initially partially disappear and gradually completely disappear. So, this is the simply phase change occurs with respect to the temperature, and that also we can find out in the solidification process. Now, progress of the phase transformation. So, that means liquid phase to the solid phase transformation is consists of the two components. First is the nucleation and the growth process. So, nucleation process, there may be the two types of the nucleation process. One is the homogeneous nucleation, another is the heterogeneous nucleation, and both these cases there are some driving forces that actually promote the homogeneous nucleation or whether it is promoting the heterogeneous nucleation. So, we will try to find out what are the driving motive for these two types of the nucleation process that we generally observe in general the solidification process or in specific to the welding. So, homogeneous nucleation, it starts with the formation of the critically sized solid from the liquid. Now, the driving force for the homogeneous nucleation is basically the undercooling, high amount of the undercooling without any external interface. So, if we purely the basic elemental part of the homogeneous nucleation is simply driven by the presence of the undercooling, but how it happens the undercooling. So, if you look into this curve during the cooling process, it is this line indicates the actually the melting point, or that means that temperature actually decides the transformation from the solid phase to liquid phase or vice versa, liquid phase to solid phase. But during the cooling process, this before change of the phase, the material may subjected to locally let us say amount of the undercooling. So, that is the with respect to that melting point, this is the amount of the undercooling that represented by the delta T, that is the below the phase change temperature. Now, once this achieves some undercooling and it starts the nucleation process, and then after starting of the nucleation process, and then it's exactly come back to the equilibrium temperature, that means the temperature that decides the phase change between the solid and liquid. So, reach the equilibrium temperature and then it's change the phase, and finally, then evolution of the latent heat is basically starts after the undercooling of this system. So, then it starts this point, reach locally achieve some amount of the undercooling and then release the latent heat, and then finally, it follow the cooling to the gradually after changing of the phase, it gradually cool to the ambient temperature by releasing the specific heat in this case. So, this undercooling is the main driving forces, and that undercooling is specifically responsible for the homogeneous nucleation process. That nucleation actually happens throughout the structure at a time. But of course, this undercooling actually reach or achieved in a very local position within the pool of the molten pool, within the pool of the liquid metal, at which point there is a undercooling. Several point can be undercooling locally, some amount of achieving this undercooling, and that once it achieves the undercooling, then it starts the nucleation process. So, this type of nucleation process is mainly known as the homogeneous nucleation process. Of course, there is another nucleation process. So, in this homogeneous nucleation process, probably there is no role of the external surface. So, presence of external surface, that is maybe adjacent to the liquid metal or maybe some interface with the liquid metal, that actually that also actually acts as a sites to create the nucleation process. But if we try to theoretically look into the homogeneous nucleation process, so here the driving force of the homogeneous nucleation process is only the undercooling. So, the degree of undercooling is more. So, tendency of probability of formation of the nucleation, homogeneous nucleation will be more. So, in this case homogeneous nucleation, the role of the external surface is no more there. Now, if you look into in little bit about the theoretical aspects of this nucleation process, probably then it will be more beneficial to understand the solidification process in welding. So, we try to bring these two things. So far, we understand that solidification in a simple way. We understand that there is simply change of the phase from liquid phase to solid phase, that may happen one single point temperature, or that may happen over a range of the temperature, whether it is pure metal or whether it is some alloy system. Now, if we define the volume free energy, that is the free energy difference between the liquid and solid phases, because during the solidification process there is a change of the liquid to the solid phase. So, during this change of the phase, some amount of the volumetric energy is required to change from liquid to solid. So, that is can be defined as a volume free energy. But another surface energy, that is also energy needed to create a surface from the spherical particle. If we assume some spherical size of the nucleus as a sphere, so for the spherical particle, what is the amount of the surface energy is needed to create a surface, basically energy needed to create a surface. So, that means total free energy change in this process is consists of the two components. One is that over the volume over the surface. So, that is over the volume, the first component 4 by 3 pi r cube, that represents the volume of a spherical particle, and delta G V is the volume of free energy. Change of the free energy is required to change from solid to liquid phase, and that with per unit volume. So, that means volume free energy, this is the first component, is the second component is the surface energy. So, 4 pi r square is the area of the surface for a sphere or spherical particle, and gamma is basically the specific surface energy of that particle. So, that delta G represents the total free energy change during the nucleation process probably. Now, this free energy change can be represented graphically, that if you look into the graph also, here you can see that one component, that this one, that actually representation of the volume free energy change during this change of the phase from solid to liquid to solid phase. So, it is a negative we consider, but that because this actually represents by the difference the liquid and the solid amount of the energy needed, the difference between the liquid and the solid phases. So, it is a negative quantity, and other is the second component, that is the surface energy to create a surface of a spherical particle. So, this is growing positively, that means amount of change in this thing. Now, overall total free energy change can be represented like this. That means, initially total amount of the free energy is actually balancing between this surface energy and the volume energy. So, balancing these two, it is initially growing and it reaches some maximum point, and then again amount of the energy actually reduces, and finally it reaches to the negative value. Now, from this typical nature of the energy total energy free energy change during the nucleation process, we can find out that this optimum point is the amount of the optimum energy, that this amount of the optimum energy is the maximum amount of the energy is required to form a stable nucleus. So, that optimum point of the optimum energy level actually decides what may be the size of the nucleus, so that it can sustain, and that this critical energy simply estimated by the first derivative of free energy, total free energy change, making is 0, and then from this we can find out that size of the nucleus. In this case, the critical size is basically can be represented in terms of the specific surface energy and the volume free energy. So, that R star equal to minus twice lambda by delta G V. So, that it is a ratio of the surface energy by the volume free energy. So, that means these two types of the energy actually decides what may be the critical size of the nucleus, so that nucleus can grow further. But what is the total maximum amount of the energy or optimum amount of the free energy change, that is also related to that the surface energy and the volume free energy in these cases. Now, critical size of the nucleus, it is some negative sign is there, that means it is depending on the what is the sign convention, what we can consider is the delta G V. So, because of that time sign convention, that negative sign is there, but we can consider the magnitude of this size of the critical nucleus. It is a ratio of this 2 times of the ratio of this specific surface energy and the volume free energy to change volume free energy related to change from the liquid to the free energy difference between the liquid to the solid phase. Now, this amount of the optimum amount of the energy or is also represented in terms of these two components, that volume free energy and the specific surface energy. But if we see that volume free energy can also be represented in term, also depends on the latent heat and the degree of undercooling that means the temperature difference between the equilibrium solidification temperature. So, that means equilibrium solidification temperature maybe you can assume at is a phase change temperature, single point phase change temperature, and it is the latent amount of the latent heat. All this actually decides the decides the amount of the free energy difference between the liquid and the solid phase for a specific material. Therefore, delta T can also be represented by the temperature, the phase change temperature, and T is the temperature in between. For example, here it is can be represented the equivalent solidification temperature, and T can be any intermediate temperature T. So, that the T m minus T is basically represents the amount of the supercooling here. So, or L is the latent heat. So, this is the typical calculation of the size of the or amount of the energy required to start the nucleation process or the stable nucleation process. What is the energy barrier probably required in case of the homogeneous nucleation process? These are the typical expression of the size of the nucleus and what is the optimum amount of the free energy change is required to start the nucleation process of stable nucleation process. Now, heterogeneous nucleation also to some extent that it is also formation of the critically sized solid from the liquid, but that formation of the critically sized nucleus happens from the pre-existing sites or in the pre-existing or in presence of the any surface or the in presence of the interface, the heterogeneous nucleation starts. So, driving force or maybe here the driving force may be the different in case of heterogeneous welding process, but the in case of heterogeneous nucleation process any kind of inclusion presence in the liquid metal or any interface or any surface, they actually start they actually initiate the at this point there is a initiation of the nucleation happens in case of the heterogeneous nucleation process. So, if we simply represent that what is the amount of the optimum amount of the energy required in case of the heterogeneous nucleation process, that is the amount of the energy optimum energy required for the homogeneous nucleation process into some factor that S is the as a function of theta. So, that factor S actually intuitively depend on the size shape of the nucleus, because when the heterogeneous nucleation happens based on the nucleation theory over the interface, the surface tension between this interface or surface and the liquid metal can be different as compared to the only the surface tension of the completely solid metal when it is the solid metal exists within the liquid molten pool. That happens in case of the homogeneous nucleation process. So, that is why depending upon that S theta is the shape of the nucleus, and of course, this as a function of the shape of the nucleus, and this S theta can vary from 0 to 1 in between 0 to 1. So, if we typically plot the total free energy change in case of homogeneous nucleation process and in case of heterogeneous nucleation process, we can find out the difference here. Here we can see that amount of the heterogeneous nucleation process, the barrier to start the nucleation process is less in case of the heterogeneous nucleation as compared to the homogeneous nucleation process. So, this amount total amount is the amount to critical amount of the energy required for the to start the homogeneous nucleation process, and this is only the small amount that start the nucleation process in case of heterogeneous nucleation. But critical size of the nucleus both the cases is the same, because that the critical size of the nucleus is intuitively depend on the volume free energy and the surface specific surface energy of the material of the particle basically. So, that is why it is the critical size of the nucleus is independent of the shape of the nucleus. Now, we will try to look into that solidification in case of the binary alloy system. So, here the liquid of the uniform composition rarely uniform after the solidification, because we assume the liquid of the uniform composition, but after the solidification it may not be the uniform, and solute atoms in the liquid, the redistribution solute atoms in the liquid, that also happens, the redistribution of the solute atoms during the solidification process. So, redistribution of the solute atom in the solidification process in specific to binary alloy, that actually depends on the thermodynamics, that means phase diagram, and kinetics. Kinetics means the diffusion, undercooling, and in any material flow. Of course, undercooling, these are the kinetics, and that fluid flow, all these are the influencing factor for redistribution of the solute atoms in case of the binary alloy system. Now, if we look into one typical phase diagram, binary phase diagram, here if you see that there is a liquidous line, and we representing the liquidous and solidus line as a straight line. So, and if we pick up any initial composition of the solutes, x axis represents the solute concentration and y axis represents the temperature. So, at any solute concentration, so if we assume the initial solute concentration at this point C0. So, at this point if you draw one vertical line, so this point corresponds to that liquidus temperature, and this point corresponds to that solidus temperature. Similarly, if we consider the concentration are different, the liquidus and the solidus temperature can be different depending upon the liquidus line and the solidus line, and for a with the different composition. So, with this composition, the liquidus line here equal to TL, and solidus temperature is basically it represents by the Ts, and at any temperature in between the solidus and liquidus, because between the solidus and liquidus temperature there may be the solid content and the liquid content. So, at any temperature in the case of the initial concentration, initial composition of the binary alloy is the C0. So, in between temperature, so this represents the liquid content. So, that means with respect to the any temperature line, if you draw one horizontal line, so that actually cross the liquidus temperature and solidus temperature. So, that liquidus temperature, this point correspond to that, this actually represents the liquid content, and which that at that point corresponds to the solidus line, that actually represents the solid content. So, that means we can say that although initial composition of the metal is concentration is C0, so in between the liquid and solidus temperature, that consists of the liquid content and solid content. So, that can be this amount, the solid content and liquid content can be evaluated simply using the simply in a proportionate way. We can usually find out what is the amount of the liquid composition, what is the amount of the solid concentration within on a specific temperature. So, here also you can see that C0, and that when this C0 composition corresponds to the liquidus line, when it cross the liquidus line, liquidus it cross the liquidus line, and that corresponding point, if you draw one temperature line, the basically liquidus temperature. So, which point it cross that solidus line, this composition is corresponds to the K into C0. So, definitely here K should be the less than 1, that means less than 1 means their liquid content for this case in this case is basically less than C0. Now, if we further discuss on the phase diagram, so we assume the initial composition C0, and the solidification starts when the liquid cools down to the TL cools to the TL. So, solidification starts because at this composition, and solidification when it cools to the TL, the solidification when it comes to the some superheating temperature, and when it comes at this point, the TL point, exactly the solidification starts, and gradually it solidify, it comes to the solidus line, then we can say the solidification complete. That means, in the solidus line it is a the phase is completely solid phase, but the concentration in composition of the concentration is exactly at the same amount C 0. It is simply following this vertical line. It starts from the solidification starts at this point and gradually it reach this point, that completes the solidification. So, we can analyze by using the lever rule in between the solidus and liquidus temperature, we can find out the composition, that means liquid content and the solid content from this binary phase diagram. Now, what is the typical point at that? So, at any temperature T, the Cs and Cs represents the solid content and Cl represents the composition of the liquid and basically the here the coexisting of the liquid and the solid phase here. Now, at equilibrium temperature T, the partition ratio or the equilibrium segregation coefficients between these two, that K can be represented, small k can be represented by the ratio of the Cs by Cl. It is a simply a composition of the solid composition and the liquid composition, but this composition corresponds to at equilibrium temperature T. So, equilibrium temperature changes T, this value of the K may change if the equilibrium solidification temperature changes. So, from this information phase diagram we can further analyze this phase diagram in case of binary alloy, that solute content of the liquid continues to rise during the solidification by lowering the solidification temperature. So, solute content by lowering the solidification temperature, if we move along this by lowering the solidification temperature. So, at this point the definitely the solute content is more if solidification temperature is less. Second point, as the solid grows from the liquid, its solute content also continues to rise. Definitely as the solid grows from the liquid, so when it starts from the liquid phase and continuously grow towards the solid phase, the concentration of the solid phase actually increases. If K less than 1, then Cs and Cl both increases as temperature T of the solid liquid interface drops during the solidification. So, when the solidification temperature actually drops, both the Cs and corresponding Cl liquid content and the solid content actually both are increases if there is a decrement of the temperature T. The slope of the liquidus line ML is less than the 0 when K is less than 1 and vice versa. The slope, definitely here we can see this diagram, the slope is basically less than 0, that slope is basically negative in this case, and K, when K is less than 1, definitely when K is less than 1, the slope is basically negative, and of course vice versa also correct. If the liquidus line is straight, then temperature T on liquidus line can be expressed as this way. So, that if you see if we can see that the liquidus line is straight, the any temperature T on the liquidus line can be expressed at this. So, if we see here the liquidus line is basically straight. So, at any point the temperature is can be T can be that melting point temperature minus the difference between the Tm and T, between that temperature. So, Tm minus T. So, that Tm minus T, the increment can be represented by the slope ML, and the slope at corresponds to the Cl. So, m into Cl and this slope is negative. So, Tm can be represented by the T at any point can be represented by the Tm negative slope and the amount of the liquid content on that specific point. So, at this specific point, what is the slope? This actually represents that Tm. This actually represents this also mathematically says that this is also equal to that slope into that content Cl. So, this amount. So, which is equivalent to that this amount. So, that way that if liquidus line is straight, not the curve here, then a temperature T on the liquidus line can be expressed like this. So, with this understanding of the binary phase diagram during the solidification process, and here we will try to look into other aspects that complete solidification in welding process, that complete diffusion in solid and liquid state. Here you can see that we assume that the material, the complete diffusion in the solid and liquid, the composition we choose in such a way that there is a complete diffusion in the solid and liquid state. So, that means if Fs and Fl actually represent the fraction of the solid and the liquid state, then according to the conservation of the solute, this should be 1. Fs plus Fl should be with respect to 1, and if we look into that figure represent that the fraction is solid fraction and liquid fraction, it starts from 0 and gradually increasing to 1, and there is a transformation that happens during the that solid is it's a solid grows from the liquid phase, and that means from liquid to solid phase, and when in that direction the solid phase is gradually consuming the liquid phase. So, that total volume, total fraction should be 1. Now, graphically you can see that at any point, so this is the solid fraction some part and some part is the liquid fraction. So, this is the liquid fraction, this is the solid fraction, and C0 is the initial composition of the initial composition of the solute. Now, here at any point, here is the Cl liquid content, and this point represents the Cl and this the solid content, that means concentration of the liquid phase and concentration of the solid phase here in this case. Now, Fs into Cs and Cl into Fl basically represents the amount of the solute in the solid and the liquid phase. So, that total area with respect to C0, if you see the total area with respect to C0 is basically Fs into Fl into C0, the area represents, and which is corresponds to the amounts of the solute in the solid phase and amount of the solid in the liquid phase. So, that means it is equal to the area occupied by the solid phase plus area occupied by the liquid phase. So, that total content should be equal to the with respect to the C0. So, Fs plus Fl is simply 1 according to the solute conservation, and that means it is equal to C0. So, from this equation we can easily find out by applying the lever rule what is the solid liquid fraction and what is the solid fraction in this case. And of course, composition of the liquid also can be represented Cl C0 in terms of the K also, because K actually represents the ratio of the Cs by Cl. That means liquid solid content and the liquid content of this. So, in terms of the K, so here we can find out the Cl equal to in terms of the C0 fraction of the liquid and K in terms of K, and as well as the in terms of the fraction of the liquid we can write all these things. So, that is In this way, we can represent the changes, the fraction of the solid and liquid during the transformation from the solid phase to liquid phase, specific to the in case of the binary alloy system. Now, if we look into that, during this solidification process, the different types of the grain structure we can expect. Normally, one is that equiaxed kind of grains, that in this equiaxed kind of grains, if we see that equiaxed grain, if we consider the pool of the molten pool within the container, then the surface actually acts as a heterogeneous nucleation process. So, along the surface we can find out the almost equal size of the grains. So, crystal grows almost equally in all the directions, and that is the commonly found out in the adjacent to the cold metal wall. So, around the cold wall, this there is a formation of the equiaxed grain structure. Similarly, we can find out the columnar grain structure. It is basically long and very thin, created under the steep temperature gradient. So, temperature gradient, high temperature gradient is oriented on specific direction, and that actually driving force make a columnar type of the grains. So, definitely columnar type of the grains is relatively slow as compared to the equiaxed type of grains, because equiaxed type of grains more or less actually happens throughout the whole throughout the surface, is almost at the same time. And another point is that columnar grains actually grow perpendicular to the surface, and entirely it depends on the definitely this columnar types of the grain, it depends on the directed temperature gradient or high amount of the temperature gradient in specific direction. So, this easily form kind of grain structure normally we observe in the solidification process. And here we can find out that other type of binary alloy system, but here no solid diffusion and complete diffusion in liquid we generally observe, and one case is the no solid diffusion and limited diffusion also observed. So, in that case the behavior of the solidification becomes more complicated. So, here these two types of the solidification behavior is beyond our scope. Now, if we look into the what are the different types of the solidification modes. So, during the solidification of a pure metal, the solid liquid interface is usually planar type thing. So, there is a front moves in say making like a plane. So, that is the one type of mode, but normally for an alloy system, the mode of the solidification in the solid liquid interface can be the planar type of, it can be cellular, it can be dendritic type of the mode, depending on the solidification condition and the material system involved. So, we will try to look into the different types of solidification mode, generally observe these things. So, first one is the planar mode. So, that solidification front exactly moves making a plane and gradually moves. Cellular, there is a breaking of the planar mode, and it can make a kind of structure like looks like a cell kind of structure. So, this is the cellular type of solidification modes. Another third is the columnar dendritic type structure. So, its growth is a kind of columnar one direction, but the dendrites forms is a primary dendritic, secondary dendritic arm can also be formed. So, this is the typical columnar dendritic type of structure may also solidification mode can also be observed. Another is the equiaxed dendrite. So, of course, the dendritic structure exists within the one grain, but there are several positions almost equal size of the grains exist within the each grain. There may be the development of the columnar type of the dendritic structure, maybe the dendritic structure observed within the equiaxed structure. So, these are the typical solidification modes we normally observe, but if we look into that, here solidification and welding, but to analyze these things, that little bit the quantitative analysis of the solidification, we can look into that constitutional supercooling.